Okay, we are on air. So hello everyone and welcome once again to the Latin American Webinars on Physics. I am Joel Jones from the PUCP in Peru and I'll be your host today. You might have noticed that today is quite a special day. Besides having the webinar and getting a break from the World Cup, we're also celebrating the 6-year anniversary of the discovery of the Higgs boson. So that means that if you needed an excuse to bake a birthday cake, now you've got it. Anyway, considering such a special occasion, it is very appropriate to have Juan Carlos Helo as our speaker today. Juan Carlos is a professor at the Universidad de La Serena in Chile. He did his PhD at the Universidad Federico Santa Maria in Valparaíso, also in Chile, and immediately became a junior professor afterwards. In 2016, he transferred to La Serena, which is a university which will acquire particular relevance once the Andes lab is finished. So, today, Juan Carlos will talk about high-dimensional neutrino masses. This is webinar 66 in our series. So I'd like to remind you that if you want to be part of the discussion, you can write questions and comments via the YouTube live chat system. So, I think that's everything for the introduction. I will now hand you over to Juan Carlos. So here you go. We're all yours, man. Oh, sorry, we've muted you. Let's see. Okay, now you can speak.
Okay. Hello. First of all, I would like to thank you for the invitation to talk in the Latin American webinars on physics. Very happy to do it. It's my first time. I'm going to share the screen. Presentation. You can see the presentation, right?
Everything good.
Okay, perfect. So today we'll talk about neutrino mass models generated by high-dimensional operators. This talk is based on 3 papers I wrote in collaboration with Gaetana Namiati, Oscar Castillo, Renato Fonseca, Martin Hirsch, and Ricardo Cepedello. Well, in the past 15 years, neutrino physics has revolutionized our understanding of particle physics. The discovery of neutrino oscillations implies that neutrinos have masses and miss each other. This is the only particle physics evidence of new physics beyond the standard model to date. The observed smallness of the neutrino masses is usually attributed to a large value of the scale of lepton number violation, typically of the order of 10 to 15 gigaelectron volts. This is the essence of the seesaw mechanisms, in which, with a large mass scale, we generate tiny neutrino masses. While this mechanism is simple and elegant, the larger mass scale involved in this argument makes the direct test of the classical seesaw mechanism impossible. There exist, however, many possibilities to explain the smallness of neutrino masses with lower lepton number violating scales. In order to do this, it is necessary to have additional suppressions, such as neutrino masses generated by higher dimensional operators and or a different loop level. One can write in general Majorana neutrino masses in terms of the dimension of the operator D and the number of loops n as in equation 1. Here V stands for the standard model vacuum expectation value. This equation can be used to estimate the typical lambda scale, for which the observed neutrino masses could be explained for a given dimension D and loop number n. This figure illustrates this estimate. The energy range have been estimated using average Yukawa couplings in the range of 10 to minus 2 to 1. For this figure, we can see that for dimension 5 operators at 3 level, the typical scale goes from 10 to 10 to 10 to 15 gigaelectron volts. These are the seesaw mechanisms which correspond to the liberalisation of the dimension phi operator. As the number of loops increase, the energy scale decrease. Same is true for higher dimensional operator from dimension 5 to dimension 13. In this figure, we also show the estimate reached for colliders. The left line is roughly 100 gigaelectronvolts after the negative search performed at the left collider. The horizontal gray band indicates a very rough estimate of the reach of the LHC. The lower edge of the band corresponds to per production of sharp particles, while the upper edge is roughly the reach of the LHC for particles produced in its channel resonance. For dimension 9 and larger, one expects that the LHC experiments will cover an important part of the available parameter space of these models. Thus, neutrino mass models generated at dimension 9 and higher should be testable in the near future. These arguments form the main motivation of our work in this presentation. The dimension 5 Weinberg operator can be generated at tree level in exactly 3 different ways, which correspond to the 3 types of seesaw mechanisms: type 1, type 2, and type 3. These 3 different models share the same diagram topology. So, for dimension 5 operators, we have 1 possible topology and 3 different possible models, as discussed in this paper by Ernest Mann. Now, at dimension 7, one already finds 4 different topologies, which lead to several model realization, as is discussed in these papers. In order to make these dimension 7 tree-level neutrino mass models to be interesting, it is necessary to forbid or suppress lower order contributions, which are in this case the dimension 5 tree-level seesaw mechanisms. This can be done simply by the fact that the particle content does not allow lower order contributions, or by imposing additional symmetries. In our work, we focus on the first possibility, models in which lower order contributions are absent only due to the particle content. It turns out that for the tree-level dimension 7 neutrino mass models, there is only 1 model for which the dimension 5 tree-level seesaw mechanisms are absent without the need of imposing any additional symmetry. This is the model shown in this figure. This model contains 2 new particles, as shown in this figure. 1 triplet fermion with hypercharge 1, which is this particle over here, and 1 scalar, which is quadruplet in SE2 representation with hypercharge 3/2. We call this type of models genuine, in the sense that lower order contributions are absent without the need of imposing any additional symmetry. We analyze systematically all tree-level decomposition of the dimension 9, dimension 11, and dimension 13 neutrino mass operators with the same logic that before, trying to find genuine models. The complete list of diagrams can be found at this link in the webpage of Renato Fonseca. For dimension 9, we found 18 topologies and 66 diagrams. However, among all these, there are only 2 genuine neutrino mass models, which are shown in these figures. These models are genuine, therefore, the tree-level dimension 5 or dimension 7 diagrams, or the 1-loop dimension 5 diagrams are absent only due to the particle content. without imposing any discrete symmetry. Let us note that for these models, one Majorana fermion, which is akin to the necessary representations, appears. At dimension 11, there are 92 topologies plus 504 diagrams. The number starts to increase very, very fast with the dimension of the operators. But again, there are only 2 genuine models. At dimension 11, genuine diagrams require at least 4 different beyond standard model particles and large SU2 representations. At least 2 different quintuplets are needed, and the model shown here in the right requires a sectet. Now in dimension 13, there are 576 topologies and 4,199 diagrams. The numbers start to increase very fast, as I already said. But the numbers of genuine models still remains very small, 6 genuine models. Here we show the 6 genuine models in a compact way. Let us note that they require to have Majorana fermions in the middle, which could be a quintuplet or a septet. And for the diagram in the top, one can make a exchange of Higgs with the Higgs dagger, replacing the quadruplet fermion with hypercharge 3/2 by a quadruplet fermion with a hypercharge 1/2. Changing one or both of these quadruplet fermion, we get the 6 possible models. Let us note that for dimension 9 and dimension 13, there are genuine models with Majorana fermions in the middle of the diagram, which will lead to very interesting phenomenology, which we will analyze in future papers. Let us now discuss one liberalization of neutrino mass models. The author of this paper systematically analyzed all one-loop dimension 5 topologies. In total, they found that there are 6 topologies, but only 2 of them, which they call T1 and T3, can yield genuine models in our sense. This leads to 4 different diagrams shown in this figure. The well-known C model corresponds to T12, this one. An example for T3 is the scotogenic model, which has a right-handed neutrino and a doublet scalar in its particle content. The scotogenic model is not genuine in our sense because it requires an additional C2 symmetry in order to forbid the true-level dimension 5 seesaw type 1 mechanism, which otherwise will be generated by the presence of the right-handed neutrino. In contrast to the true-level diagram, for one-loop diagrams, the representation and the hypercharge of the internal particles are not uniquely fixed. This leads to a series of possible models at one loop, if one allows for larger SU2 representations and hypercharges. We also, in our works, we analyze the dimension 7 one-loop models in a systematic way. We found 48 topologies, from which, however, only 8 can lead to genuine models. In total, there are 23 genuine diagrams. Among these genuine models, there is only one diagram in which the largest internal representation can be as small as a triplet, while there are a further 22 diagrams with at least one quadruplet. These figures are showing 2 example models which contain triplets and quadruplets as the smallest representation. These 2 examples are one-loop dimension 7 genuine neutrino mass models. This means that the true-level dimension 5, the true-level dimension 7 diagrams are absent, only due to the particle content of these models, without the need of imposing any additional symmetry. Again, as in the case of the dimension 5 one loop, one can build series of models allowing for larger representation and or hypercharge for the particle in the loop. Here is the triplet model, the sampling that we analyze in more detail, the Lagrangian of the model and the particle content. As we can see, it has a triplet fermion with hypercharge 1, a one doublet fermion with hypercharge 5.5, and 3 additional scalars, doublets, 2 doublets, and 1 triplet. We studied the phenomenology of this triplet model and also the quadruplet model in detail. As is well known, experimental upper limits on lepton flavor violating decays provide important constraints on TV scale extension of the standard model. In this figure, we show results for calculated branching ratios of mu going to E gamma, mu going to EEE, and mu E conversion for different choices of parameters as a function of one of the Yukawa couplings, in this case, Y3. The horizontal full lines show current experimental limits, and the horizontal dashed lines future expected sensitivities. The non-observation of lepton flavor decays can be used to put upper bounds on the Yukawa couplings of our models. At the same time, the observed neutrino masses require lower bounds on these Yukawa couplings, and the combination of both constraints results in a very restricted range of allowed parameters. We also analyze constraints from LHC searches. A number of different LHC searches can be used to set limits on the various particles of our examples models. The simplest search, and currently the most stringent LHC limit for our models, comes from a recent Atlas search for doubly charged particles decaying to either EE or mu final states. Results of our calculations compared to the experimental limits are shown in this figure for the mu final state. Here we have the cross-section of per production of eta 1 double charge scalar decaying into mu's versus the mass of the double charge scalar. Scanning over the allowed neutrino parameters then leads to a variation of the branching ratios of eta 1 into different lepton generation. This explains the spread of the numerical calculation point in this figure. Combined with the experimental limits from Atlas, lower mass limits in the range of 680 GeV result. I now turn the discussion to possible lepton number by lepton signals, or the LHC. This table shows examples of different lepton number by lepton states from per production of scalars or fermions in the two models under consideration. The table gives in column 1 the multiplicity of the final states, and in column 2 the lepton number by lepton signal. These final states are produced from the decay of the particles given in column 3. These particles can be produced in per production at the LHC, and they can decay into the lepton number by lepton signals in the second column. Observation of this lepton number by lepton signal is only possible if both branching ratios have similar value. For instance, for this scalar, which is a 4-charge scalar in the triplet model, can be produced in per production and can decay to 4 leptons with the same charge in one branch, in the other branch to 2 leptons with 2 Ws, generating a signal that dilates lepton number by 2 units. If we want the lepton number by lepton signal to be possible, it's necessary that the branching ratio of these 2 possible channels to be of the similar order. Here in this plot, we show the ratio of this branching ratio as a function of the lambda 2 coupling of the triplet model. for some fixed choice of the other parameters and different values of mu1. One can see from this figure that the equality of branching ratios is naturally possible for different choices of parameters without the need of any fine-tuning. Same is true for the quadruple model, as is shown in this other figure. Well, finally, the conclusions. In our work, we discussed the systematic deconstruction of dimension 9, dimension 11, and dimension 13 neutrino mass operators at tree level. From all the possible diagrams, we found only 10 genuine models, 2 models at dimension 9, 2 models at dimension 11, and 6 models at dimension 13. We also discussed neutrino mass models at one loop dimension 7. We found 23 diagrams that lead to genuine models. Only one possible diagram for which the larger necessary representation is a triplet, and the remaining 22 diagrams with the larger representation being at least a quadruplet. We study the 2 examples in detail, one triplet and one quadruplet model. New lepton number violating final states appears. In particular, final states with large multiplicities are predicted to occur. Thank you.
Okay, thank you very much. Let me get back. Okay, so thank you very much for the very nice webinar. So we are open to questions. So let's start with the audience right now. Oh, have we lost Juan Carlos?
I'm here.
Oh, here you are. Oh, here you are. Okay, sorry.
One question from here.
Yo, go ahead.
Hi, Juan Carlos. What happened with the dark matter in the genuine model? There is a dark matter candidate there, or all the particles are unstable?
Yeah, that's a good question. In principle, for the one loop dimension 7, genuine models could be candidate of dark matters in a similar way that I believe that you wrote a paper for dimension 5, right? With dark matter? Or yes. So in principle, but we didn't analyze in detail those possibilities for the one loop dimension 7. But in principle, you could have genuine models with dark matter in the particles in the loop. Yes. So that's an interesting direction to analyze.
Okay. Any more questions over here? Okay, so I have a simple question. So when you talk about your genuine models, right? You said that no additional symmetries, all of the operators are generated by the introduction of new particles. So can you have 2 genuine models simultaneously, giving you contributions to the same effective mass, say the same this equals 7 mass?
That's a good question. For instance, I'm going to share the screen again. No, well, can you show one slide?
Go ahead.
In this case, so I'm sharing the screen, right?
Yes.
So here you have 2 different genuine one loop dimension 7 neutrino mass models. However, if they are together, you will get you will have a diagram which is a dimension 7 at tree level, which is actually this one, because this one has the quadruplet scalar with 3½ hypercharge, this one, and one fermion which is a triplet with the hypercharge 1, which is exactly what you have here and here. So if you have these two diagrams at the same time, they won't be genuine anymore, because you will generate the dimension 7 tree level.
Right. They will not be genuine one loop models.
Yes. It won't be, the one loop won't be genuine. Yeah, exactly. They won't be the leading order contribution anymore.
I see.
Because you will have a lower order contribution, which is the tree level dimension 7.
So also in this direction, so when one works with this TV scale CISO models, one finds that there are that the loop corrections to the neutrino masses can be important, right? So basically, you have some other lepton number violating parameters that don't appear at tree level, so they're not constrained by the neutrino masses, but they appear at loop level, so they can give large contributions to the neutrino masses. So that can constrain these TV scale CISO models. So I was wondering if you have checked that this situation will not arise in this kind of models.
Yeah, and I mean we focus on the. I mean, in principle, you can have, for instance, loop diagrams which are more important than the tree level diagrams at the same level operator, but you need to play with the couplings. If you put couplings very small for the tree level, of course, the contribution will be very small. So we are not analyzing that situation, but that situation is also possible and also interesting. So we are not saying that all the other cases are not important. So we analyze one criterion, which is more or less saying that the couplings are of the same order, and under that criteria we define this genuine condition. But in principle, yes, you can have situations when the loop is more important than the tree level, only because some couplings you are putting very, very small in the tree level, for instance.
Fantastic. Thank you very much. I don't know if there are any more questions.
Yeah, I have a very naive question. Juan Carlos, in the case of one of these models can be compatible, for instance, with some realization for leptogenesis or something like that, in the sense that you need to, in the case maybe you have some scalar that one part gets very heavy, the other light enough to contribute to the loop, not to.
Yeah, I have no thought in that direction, but maybe it's probably, yeah, but I have not analyzed that possibility at all.
Okay, thank you.
All right. Any more questions? Let me check the YouTube.
Yes, in the first question of Joel, do you mention that one to loop diagram dimension 9 or so was also generating a tree-level contribution? At the end, how do you avoid the tree-level contribution?
Sorry, can you repeat me the question again?
Yes, in the slide that you're sharing now,
yes,
the diagram of the left, in principle, has also one tree-level contribution.
No,
because of the presence of the quadruplet.
No. In the left, you don't have a quadruplet.
Ah, sorry, in the right.
In the right, you don't have the triplet. Let's say. So both separately, they don't have a tree-level contribution, not dimension 7, not dimension 5.
Could you remember me when the tree-level contribution appears in the previous answer? How the tree-level contribution appears?
Sorry?
Do you mention before that with some combination of these two diagrams or so on, the tree-level contribution reappears?
Yes. So the genuine 3-level dimension 7, which requires to have a quadruplet scalar with 3 hypercharge, which is this one over here, and one triplet fermion with the hypercharge 1, which is this one.
Okay.
So if you want to have these two diagrams at the same time, you will have also unavoidably, at least you put an additional symmetry, of course, at 3-level dimension 7. So those two diagrams won't be the leading order contribution anymore. However, if you analyze them separately, they will be the leading order contribution.
By the way, in this kind of diagrams, the hypercharge of the multiples seem to be very high. Some is in principle incompatible with having a dark matter candidate. Do you have any example with something that can have one hypercharge compatible with some neutral dark matter like state?
Yeah. As already said, I didn't analyze that in many detail, but you have some freedom in the loops. So you can change the hypercharge and also the SU2 representation. So in principle, you can play around with these numbers in order to find this dark matter candidate. So in principle, you can play with that. We didn't do it, but in principle, it is possible.
Okay.
I have one very short question.
Go ahead,
it's just Juan Carlos, in your analysis, let's say that you focus mostly to generate the masses in the case of Majorana neutrinos.
Yes.
So have you considered, for instance, other realization, maybe not for double beta decay or something like that, but in the case of Dirac neutrinos, if there is a kind of similar classification of?
No, we didn't consider. In principle, you can think in that direction too. Yeah, but we didn't do that.
Oh, okay. No, just to know, because in principle with the Dirac neutrino, you have to add some symmetry in your model, no? So this is, I would say, I don't know. But yeah, of course, in the case that you analyzed, you didn't have any other extra symmetry. For that reason,
yes. Yeah.
So nice the analysis that you presented.
Yes. Just a comment after the first word of Juan Carlos, there appears in fact one paper about the dimension 7 case of Dirac neutrinos. I don't remember now the specific reference, but there is some study already on this line.
Okay, good. Yeah, I think we could think it could be something analogous for the Dirac, but I haven't thought about it. Yeah, so you can send me the reference, Diego.
Yes, of course.
Hello, can I ask a question?
Yes.
Maybe naive, but in your case, you have couplings order 1, right? Or, I mean, not too small, and
yes.
masses which are relatively light. So what about the Hicks couplings? I mean, for instance, like the triple Hicks coupling would be probably quite, I expect to have changes on the Hicks couplings due to the new particles and charges which are relatively large or not?
Yeah, you mean, for instance, this one, the quadruplet? Right. Yeah, this is, or this one, 2 Hickses with 2 scalar.
Yeah, it may be a naive question, right? I'm asking.
No, it's a good question. I think here in this plots, this is for the triplet model. So mu1. This mu1, let me go up here. Mu1 is the coupling among the 2 doublet scalars. It's the coupling among this doublet scalar with the Higgs. It's mu1. And this mu1, here we set it to be 1 TeV for these 3 plots, for instance. And here we play with this mu1 from 1 giga-electron volts to 100 giga-electron volts. So basically, we give them some freedom from small values to larger values.
Okay. Okay, thanks.
Okay, so let me ask one question. So have you looked at tau mu gamma, tau e gamma? Is because I mean,
No,
usually one expects that mu e gamma, mu e conversion will be the dominant sources of constraints, right?
yes, that's why we didn't. I mean, we use Spheno to calculate this. So in principle, Spheno gives you all with this flavor. So we had all the numbers, but the most stringent came from this 3-1. So that's why we.
It's a shame because with the Bell 2 experiment starting, you know, they will be putting new bounds in this lepton flare violating tau decays, but still it seems that there are not many models around that I have seen at least that can use these bounds.
Yes, true.
Okay, I don't know if there's any other question. Okay, and in the chat, okay, nothing in the chat. All right, so thank you very much, Juan Carlos, for the very nice talk. And let me remind you that in 2 weeks, we have Cosimo Bambi giving a talk. I don't remember the topic, but it's probably something related to general relativity or gravity, something, modified gravity, maybe. Anyway, so we'll see you then. Okay. So thank you for listening, and thank you, Juan Carlos, for the talk.
Thank you for the invitation. Very happy to give it the talk.
See you around.
Bye bye.